Swayam Prabha. Digital India. Educated India.
Welcome all of you for these very interesting lectures on Bernoulliâ equations and its applications. The last class we discussed about Bernoulliâ equations, starting from its history of Bernoulliâ equations. Very briefly I can say that because of the Bernoulliâ equations having a simplifications to the fluid flow problems, the industrial revolutions what it happened in Europe, the contribution of Bernoulliâ equations also helped a lot to design pipe flow, channel flow in Europe after these equations was suggested long back in 1752. Now, today I will give a very simple way representation of these Bernoulliâ equations, how we can use for real fluid flow problems with some correction factors, or we can use these Bernoulliâ equations as a hydraulic gradient line, energy gradient line, and we can apply these equations for a systems having pump and the turbine. So, basically today I will talk more applications and how we can use the Bernoulliâ equations for real fluid flow problems. That is the basic concept what I will do, and these are the reference books, and most of these materials partly we follow from Sinjal Simbala and F.M. White book. I will start with the applications, very interesting applications I will show to you. Then I will go for orifice meter experiment in IIT Guwahati. Then I will talk about kinetic energy corrections factors. That means, for a non-uniform distributions of flow, when you apply these Bernoulliâ equations, we need to have a corrections factors if we are using average velocity. That correction factors for Bernoulliâ equations. Fourth part, I will talk about how we can define the three different types of pressures: static, dynamic and stagnation pressures. Then we will come hydraulic and energy gradient lines, that is the basic concept what we will talk about. Then I will talk about if we have a pipe flow systems with a series of pump turbine systems, then how we apply it and how we can quantify different energy, mechanical energy, also the efficiency to the fluid flow problems. Then we will solve around 4 fluid flow problems, which are the gate and the engineering service problems we will solve, which is part of the Bernoulliâ equations applications. Then concluding this lecture, we talk about how our sense of balance is there, so how it is works it. So, let us go back to very interesting examples. As you know it, people say as of now we have very fuel efficient car. That means the mostly car we talk about the drag force. If the more the drag force, then you have to have a more fuel to be spent it, fuel to burn it. So, the basic idea is to because V stands for the design velocities, area is a projected area which is more or less constant. So, rho is the density of air, only the CD can be changed. That is what it happened, the evolutions of the CD change from almost 120 years, starting from 1800s to 220. So, the coefficient of drags, which earlier is close to the 0.8, that means the force is equal to 0.8 times of rho v square into the area, that becomes reduced to the 0.15 theoretical minimum value, very close to theoretical minimum. And that because of you see the shape of the cars. Okay. As the shape of the cars are changing it, the streamline, the drag force patterns are changing. The flow around these cars when you are moving with a design velocity, that is what it changes it with a design velocity. The cars is moving with the v, which is the design velocity. On that, what is the drag force component? So, that is what if you look at, we have achieved within 100 years the theoretical minimum value, which is 0.15, very close to that. And you look the shape of the cars, what today we have, which if you move with a design speed, then we will have a drag coefficients close to 0.15, and which is a strength of the fluid mechanics evolved the automobile sectors with a very efficient the fluid cars what is today's available, and their drag ratio starts from the coefficient of drag CD from 0.8 to 0.15. That means age equivalent to 1/6. So, for example, the 6 liters of the car, if it is taking these ones for a particular distance to travel it, now we need just 1 liter of the same distance can be traveled it, because of the drag coefficients is almost 1/6. So, this is what is evolved. The evaluations happen it's from the CD equal to 0.8 to 0.15, and that because of series of the experiments done for the automobile sectors to find out what could be the best shape of the cars. So, that the coefficient of drag should be minimum or should be coming to closer to theoretical minimum value of 0.15. So, that is what it happened in the evaluations what is happened, and that is the reasons we have a fuel efficient cars available nowadays, and with a CD value close to the theoretical minimum, and this is what is possible because of the fluid mechanics as evolved with last 120 years. Now, come back to the where simple experimental setups, we generally do the measuring the flow in a pipe either in a venturi meters or the orifice meters. The orifice meter is a small device, that means it will have a circle and there is a hole inside this. This is called the orifice. In case of the venturi meters, you have a divergent zone and converging zone, but in case of orifice, we do not have a divergent converging zone, only you have a reductions of the flow area, that is what is the orifice meters. That means you have a simple plate with a hole with a constant a particular diameters, and that is what is fixed here. So, we can measure the pressure difference at two locations. One is at the pivot locations where the cross sectional area is less, and another is the upstream locations. That pressure difference, and if we apply simple Bernoulliâ equations and the mass conservation equations, you can find out what will be the discharge passing through venturi or orifice meters. But as I said it earlier, that whenever flow goes through these venturi meter orifice meters, there will be energy losses. Because of the energy losses, there will be difference between theoretical discharge and the actual discharge. Since the Bernoulliâ equations what we applied it, we do not consider the energy loss components. We consider there is no energy losses. Okay. No, the frictional resistance is more, or there is no vortex formations and all. But in the real fluid flow, there is energy losses. Because of that, what you will have, your theoretical discharge computed from the Bernoulliâ equation and the mass conservations will be more than actual discharge. So, actual discharge, the difference between these, we introduce a coefficient of discharge, that means the CD. the CD will be the actual discharge by Q theoretical discharge. The coefficient of discharge, okay, coefficient of discharge is a CD here, it is not a coefficient of drag, please do not have a confusions between two terms. If you look at this the device where we have a setup of venturimeters and orifice meters, basically in venturimeters we have a converging zones and diverging zones, and in orifice we do not have a converging divergent zones, but we just incorporated a plate with a holes, okay, with a internal hole of this. Because of that, it also create the converging zones and the diverging zone, and because of that we can have a energy losses. In a flow systems, when the streamline are converging and the diverging, definitely there will be energy losses with these systems. As the energy losses will be there, the theoretical discharge computed using Bernoulli's equations and the conservation equations will be higher than the actual discharge. That is the reasons we introduce the coefficients of the discharge, the CD value, which is the ratio between actual discharge by theoretical discharge. So, we introduce the coefficient of discharge in this, and many of the times we have to compute it what is the coefficient of discharge. So, now if you can try to understand it, that many of the times we do not go inside in these fluid flow problems within the venturimeters or the orifice meters, that how the flow streams lines are happens, how the energy dissipated happens, that what we do not look at that in depth, but in terms of these flow patterns, what is the gross characteristics in terms of energy losses, in terms of reductions in a discharge, that what we introduce as a CD coefficients, the coefficient of discharge. So, these are gross representations of change of the flow patterns, the pressure and velocity patterns. Because of that and flow structures, we do not look at very microscopically how it is changing it, but it is a gross representation. We just look at the coefficient of discharge as the relationship between the theoretical and the actuals. There is a link between now experimental work and analytical framework. So, the Bernoulli's equations is strength there, that this is the equations we can easily incorporate the experimental relationship into these Bernoulli's equations. So, that is the strength of the Bernoulli's equation as compared to the other Euler forms or other Navier-Stokes equations form, where Bernoulli's equations are very suitable, appropriate to incorporate any energy losses, energy to these fluid flow systems or taking out from the fluid flow systems. All we can incorporate it in a Bernoulli's equations, looking as energy conservation equations, looking as a energy conservation equation. But be remember, this is the equations for along a streamlines, is the momentum equations, but we are representing as a energy equations having the three terms. Now, let us come back that whenever you have a fluid flow problems like fluid flow through a pipe. So, definitely the velocity distributions is not uniform. The velocity distributions will be changed from laminar to the turbulent. The turbulent will have a logarithmic profiles and the laminar will be parabolic profiles. So, velocity distribution changes. So, what we do it that it is very difficult for us to put it as the average velocity to compute the kinetic energy, because the flow within these pipes follow having a parabolic flow velocity distributions. Now, we are looking at if I consider the flow velocity distributions, because of that velocity distribution, what is a total amount of kinetic energy? I can compute it with simple integrations considering the velocity distributions. Then I will compute it. If I consider the average velocity, what will be the total kinetic energy? And since I am going to use the average velocity, not the velocity distributions, I apply a correction factor for that, which is called kinetic energy correction factor. Let me repeat these things. What we are looking at that in a real fluid flow problems, always we have a flow is not uniform, non-uniform distributions. That means it will have either a parabolic distributions, logarithmic distributions. It depends upon the flow through pipes or open channels or in this. The flow velocity distributions varies in a space. That's so when you apply the kinetic energy, we look at the total kinetic energy, which is we can integrate over that a small dA element with this is a Marx flux, rho v dot n is a Marx flux, and this is a half rho v squares is the mass flux into v square by 2 is a kinetic energy flux. That what will do the integrations over the total area dA, and we have the kinetic energy. So, if you look at the kinetic energy computations using the V square, V average values, we will have the kinetic energy computed using average velocities times of alpha. Alpha is kinetic energy correction factors. The basically what it indicates that if you look at compute the kinetic energy based on average velocity, then what could be the correction factors for non-uniform distributions of velocity in the particular flow field condition. So, if I equating these things, then my alpha will comes like this form, which is very simple form. As you know, it V average we can compute is average velocity, we can compute like this. So, alpha can consider it V average u to the power 3 or cubic power dA, and these integrations will give us the alpha value. For fully developed laminar flow, this alpha value is about 2. Turbulent pipe flow, this is what varies from 1.04 to 1.11. That is what is the biggest problems. Many of the fluid mechanics book, they do not give the alpha value. They consider the alpha value is close to the 1, or indirectly they represent that flow is a turbulent. The alpha value variations of 1.04 to 1.11, they do not consider it, but that is not correct. Any fluid flow problems, we should compute what is the alpha value, and whenever we apply the Bernoulli's equations, considering the velocity distributions, the kinetic energy correction factors needs to be done it, and that is the value which is varies for the turbulent pipe flow and for the laminar flow, which is equal to 2 value. Now, let us come back to this Bernoulli's equations what we have derived, that in case of unsteady compressible flow, we will have the two integrals component, then we have the v square by 2 g z, which is the elevation side is equal to the constant. But in case we make it the steady and incompressibles, then we get it these three terms. As earlier I discussed it, is this summations of three energies: flow energy, which is because of the pressure at that locations, how much work is done by that pressure, that is what will be the flow energy. You have a velocity field which have a kinetic energy, and the fluid particles or virtual fluid balls staying a particular height and from a datums which gives off potential energy. So, three energy along a streamline is a constant. The sum of these three energy, flow, kinetics and the potential energy of a fluid particles along a streamline is constant. That is what we have written it. Now, in terms of pressures, if we talk about, one is static pressures, that is the pressures act on these fluid particles. Another is the dynamic pressure because of the velocity components. Please remember this rho v square by 2 we have used when you compute the drag force. Okay. And we have a rho g h z which is the hydrostatic pressure. So, we have 3 pressure components if in terms of pressure if you look it. In terms of energy we can define it as a flow energy, kinetic energy and potential energy of a fluid particles along a streamline is a constant. Now, let me demonstrate it. If I have a pipe flow, like I have a pipe flow is going through this, it has a velocity distribution. As you know it, the velocity near to wall is 0 and whatever the height of the fluid will go, this is what will be represent is me the pressure. That is what will be represent me the pressure head. That is what the static pressures. So, basically this height will be the static pressure and that is what we measure through piezometers. But if I have insert a tube and put it inside this, okay, and as the flow is moving with the velocity v and talk about this, since it is a contact, it is a fixed point, the velocity has to be 0 at that point. So, the stagnation point will be work on this. So, because of that what will happen is the 2 energy components what we have, the flow energy and the kinetic energy, that what converted to as a head, as equivalent water head or the liquid head will get it that. So, difference between these two will give us rho v square by 2, that is what is the kinetic energy head. The difference between this pitot tube and the piezometers will give us the difference of this energy rho v square by 2, but you can say that what about the potential energy? These two energies are so high that we do not consider the Z difference what we have, that may not have that significance. That is the reasons we do not consider the potential energy part, but we can measure when you have a pipe flow, we can measure using the piezometer, you can measure the pressure. Using the pitot tube, which can insert a tube and have a sharp point to rise the fluid inside the tube, that is what measures both the components, the dynamic pressures as well as the static pressures. The dynamic pressures and the static pressures. Since we know the static pressure, you just compute what is will be the dynamic pressure. The stagnation pressure is a sum of static pressures and dynamic pressure. Now, if you look at that same concept what we are talking about, as I say that the sum of the static and dynamic pressure is called the stagnation pressure. That means, whenever you have an object which is at the stationary conditions, it is a rest conditions, at that point we will have the pressures will be because the velocity at that point of the fluid flow have to the 0. So, we get is the stagnation pressures will have a 2 component, the static pressures component and the dynamic pressures component. So, that is what we get it, because pressure at point where fluid is brought to a complete stop, then we will have a stagnation pressures will be 2 components, one is a static pressure component, another is dynamic pressures component, and those equations we can rearrange it to compute it what will be the velocity. I think this is what is used in even in modern era in any aircraft's wings, you can see there are pressure sensors, and based on this pressure sensor we can easily compute it what will be the air speed. So, to measure the air speed in any modern aircraft still also use the same concept of the measuring the pressures and as you measure the pressures at this stagnation point and you know the atmospheric pressures, then we can easily find out what could be the air speed is coming that. This is the equations used for this to measure the flow velocity when static pressure tap a pitot tubes is used. This is the same concept of the pitot tubes as I explained to you. Basically it measures the stagnation pressures which have both the components, and if you have the piezometers, then you can differentiate it and find the dynamic pressures, and once you know the dynamic pressures, you can compute what could be the velocities. The flow streamline that extend from upstream to the stagnation point is called stagnation streamline. Basically these streamlines which is just come hit over this, the mouth just pinpoint of this the hole. This is what the pitot tube is, not a big instrument. Okay, this is a small tube, okay, inclined here. So there is a pressure hole, and at this point this is the pressure hole to measure it. This is the point where the stagnation pressures is developed, and that what will be the two components, static pressures and dynamic pressures, and using these with help of the manometers we can measure the pressures, and once you know the pressures, you can compute it dynamic pressures and you can compute the velocity. Is just applications of Bernoulli's equations. Now another interesting applications of Bernoulli's equation is that energy gradient line and the hydraulic gradient line. These very great simplifications of the fluid flow problems. Like you may have the fluid flow problems with different pipe arrangement, the dock arrangement and all. Any flow, as I say, that it can have the flow distributions, but as total energy along a streamlines, if you can draw a streamlines and you want to quantify how these energies are changing it, okay, that itself, as you know it, fluid flows from higher energy to the lower energy, not the higher elevation to lower elevation. Please do not have that things. The fluid flows from higher energy to the lower energy. As it flows from any pipe flow, the channel flow, any dock flow, okay, always there will be a flow which starts from the higher energy to lower energy. Whenever flow from a higher energy to lower energy, definitely there is a energy losses happens. And these energy losses, if you can quantify it experimentally, that is what I will discuss when I discuss the pipe flow, how very interestingly these energy losses in the pipe are quantified, and then you apply the Bernoulli's equations for designing total pipe network. Same way, if you know it in a different type of open channel flow, how much of energy losses has happened, you apply these Bernoulli's equations. Also, you can design the open channel flow. The basic concept here is called that we should always gauge energy gradient line, hydraulic gradient line. So, any flow patterns we have to draw the energy gradient line and hydraulic gradient. What is the energy gradient lines? Now, we are representing the Bernoulli's equations again in a different forms. It's the same things, okay. Same energy we talk about in terms of head, in terms of meter, okay. That means as equivalent, if I have any liquid will be there, how much the lift will be there because of the pressure, because of the flow energy, because of the kinetic energy, and because of the potential head. That is the reasons we define it as a head, the pressure head, velocity head and the elevations head. There is nothing else, they are all three energy, the flow energy, kinetic energy and the potential energy, constant along a streamline. And this energy gradient line and the hydraulic gradient lines, what the difference between that? Energy gradient lines consider all these points. That means you have Z1, this is the flow energy, this is the kinetic energy. If you do not have the kinetic energy or the velocity head, then we can have the piezometer lines. If you consider the velocity head, then we have a energy gradient. So, always we should have a flow from higher energy to lower energy. Okay. This case is not that appropriate, that should be the gradient of energy gradient lines, otherwise it is not possible to have a flow. Okay. If having a flow, if there is flat energy gradient line, there will be no flow. There is no flow when you have a constant energy gradient. There is no slope of energy gradient line. So, definitely there will be a slope of energy gradient line, okay, and that what is drive the flow. So, you have an energy gradient line and you can have a pitot tube and the piezometers to measure the hydraulic gradient and the energy gradient line, and then we can sketch it as an energy gradient line to get the hydraulic gradient, and many of the times you can consider a datums from where you can compute the Z1, Z2, the elevations head of the. That means we define a streamline, then we are just drawing the energy gradient lines for this streamline. For these streamlines we are drawing the energy gradient line, we are drawing the hydraulic gradient lines. The hydraulic gradient lines is not, it does not consider velocity head, it just consider pressure head and the elevations head. Just like you just put a piezometers, then you get it what is the pressure head, also the elevations head is known to us, that the what will come it. As soon as you put the piezometers, whatever the point you will come it, that what will you define as hydraulic gradient line. If I put a pitot tube, the line what will be done by the top surface will be the energy gradient line. So, whenever we design the pipe flow or channel flow and all, we need to draw energy gradient line and the hydraulic gradient line. That is what I have explained in it that. So, the basically piezometers and the hydraulic gradient line what I have said it, and the hydraulic gradient line has a sum of the static pressures and the elevations, and the vertical distance above the pipe center is measure of the pressures within the pipe. Okay. Within the pipe, what is the distance above the pipe centers is a measure of the pipe pressures within this. What is talking about this sentence is that even if you are putting it here, whatever the pressures we are getting it, that what is the pressures within the pipe, it's measured it more or less the same value. The elevations will not be that difference. This is what I explained. It's if a pitot tube is tapped in the pipe, the liquid could rise in height, which will have the static head and the dynamic head above the pipe, and that will be above of dynamic pressures of V square by 2g the velocity head part, and that what we can draw it represents the total head using energy gradient line, which represents the total head of the fluid, flow energy, kinetic energy and the potential energy. Whenever we draw a streamlines, we can compute the energy gradient line, hydraulic gradient line. So, again I can repeat it to say that energy gradient line should have a some slopes. So, then there will be the flow. The flow will be from higher energy level to the lower energy level. The velocity gradient, the hydraulic gradient may have the difference. Okay, that is the not a big problems, but the flows goes from high energy level to low energy level. And okay, we are not discussing about open channel flow here, but in case of open channel flow, the hydraulic gradient lines coincides with the free surface of the liquid, okay, because there is no pressure head. So, whatever the water surface free surface, that what will be hydraulic gradient line, and the energy gradient lines will have included the velocity head above the free surface. That means, if you consider a open channel flow, okay, this is the free surface. This free surface will be representing as hydraulic gradient line, and b square by 2g of this, b square by 2g, adding this velocity head will get energy gradient line. Okay. In case of open channel flow, because there is no pressure head, but in case of the pipes we can have a piezometers to measure it what could be the hydraulic gradient lines. Energy gradient line, to measure it we need to have a pitot tube to compute what will be these things. Now, very basic things we should understand it. When you have a pipe exit, that means flow is going out, the pressure head becomes atmospheric pressures, no doubt about that, and that is the reason the hydraulic gradient lines coincidence with the pipe outlet. So, when the pressure heads become 0, that is what we said it in case of open channel flow, when there is no pressure, its pressure is atmospheric pressure, that the surface becomes hydraulic gradient line. Exactly same way, when you are exiting, a pipe is exiting the flow to the atmosphere, that means your hydraulic gradient lines should coincidence with the pipe outlet. Mechanical energy losses due to the frictional effects, which is converting from thermal energy, that causes the energy gradient line, hydraulic gradient line to a slope downwards in the directions of the flow. That is what I try to explaining to you, that there will be energy losses whenever you have the flow systems. Okay. So, there will be a slope downward in the directions of flow of energy gradient line and also the hydraulic gradient lines. But energy gradient line should have this, but sometimes maybe hydraulic gradient may not have the slope downward in direction of the flow. The gauge pressures of the fluid is 0 at the locations when the hydraulic gradients line intersect the fluids. The same things, I think we are repeating it, whatever we have said it in the first point, this is the same point what we are talking about here, that it happens it if there is a gauge pressures. Okay. Pressures in a flow sections lies above the hydraulic gradient line is a negative. Pressure in a section when the lies below the hydraulic gradient line is positive, and the negative, that is the difference what we get it. Pressure in a flow section that lies above the hydraulic gradient line is negative, and pressure in a section that lies below the hydraulic gradient line will be the positive value. So, this whenever we will solve the pipe flow problems, we will show it how the pressures it changes negative to positive directions as respect to the hydraulic gradient line. Now, let us consider the problems when we generally use as engineers having a pump and turbine systems. As you know it, the pump is transfer from mechanical energy to a fluid by rising pressures. Okay. Transfer the mechanical energy to a fluid. So, fluid gains the energy because of the pumping systems by rising its pressures. That is the similar way the turbine does opposite things, that it takes out or extract the mechanical energy from the fluid by dropping its pressure. So, this is what are the pump and turbine. So, when you have a flow systems and a pipe networks of your campus, you can see there is a series of pumps are there to increase the energy in the flow systems, the mechanical energy in the flow systems, and the turbines are there whenever you have a hydropower projects. So, you need to have a turbine that extract the energy from the flow systems by dropping its pressures. So, increasing a pressure and dropping a pressure. Pressure itself not a form of energy, as we all say that it is just a flow energy or storage potential energy per unit volume, that is the pressures. So, if I look at this again coming back to the Bernoulli's equations, I have that's 3 terms which will be defined as an energy term. Okay. And if I have 2 points, I am differentiating between these 2 energy, the difference part will show me the net energy difference will come in. That means, for examples, I have this systems. There is a dam, the reservoirs, the water is going through a turbine and generators, coming out at the tree, then it is a release to the tail end reservoirs. So, we have a upstream reservoir, I have a tail end reservoirs, there is a connections between the pipes and in between I have the turbines and the generators. If you look at, if I take a flow streamlines, assuming the flow is comes like this and coming to this point. Okay. So, I can find out what is the mechanical energy difference between these two parts, just differentiating this energy at the 1 and 4 locations. Similar way 2 and 3 locations we can find out, and this is a very simple pumping arrangement. You can know it that we use the pumping to enhance the mechanical energy in the fluid flow systems by raising its pressures, and because of that we have a lifting the waters in a water head tanks, as you know it. This mechanical energy what we get it, and if I multiply with a mass rate, I will get the work done part. Okay, how much of work done we are getting it, or how much power we are getting it. Maximum idle power generated by turbines will be m dash and the energy part, mass flux part, which will be talk about work per unit time is the power. So, basically we are looking for the power part, which will be, since this energy per unit mass. So, we have multiplied with the mass rate to find out what will be the power will be there. So, for example, if I take it the same problems, I need to know it what is the maximum idle power generated by this turbine. Assuming it that all are 100% efficient systems, then maximum power generated from these 1 and 2 4 points, as you know it, the pressure at these 2 points will be atmospheric pressures and both are the same. The velocity at 1 and 4, the velocity becomes 0, only this elevations difference, the potential difference energy what we will get it, that what is maximum idle power generated by the turbine. Okay. But if I consider the 2 and 3, this before turbine and after turbine, at that locations I have a V2 equal to V3, Z2 is equal to Z3. Substitute this value, I will get it, the power generated by the turbining will have a mass flux and delta P, the pressure difference between P2 and P3 by the rho value. So, these are very simple calculations, you can do it. Now, whenever we have a systems, there is energy losses. We cannot convert total mechanical energy entirely from mechanical form to other form. There will be some heat energy losses, the sound energy losses, we will have the energy losses of that. Because of that, there is a efficiency loop to that. If efficiency equal to 1, that means whatever input, that is what we get the output. It's like we are quantifying what is the mechanical efficiency of the system. If mechanical energy input and output, the ratio, that is what is called is efficiency that, or in terms of loss, we can also quantify it like this, very simple talk. Similarly, way pump efficiency and the turbine efficiency, input and output. The ratio is between output to input, that is what is the efficiency of the pump or the turbine. The mechanical power increases of the fluid by mechanical power input, turbine mechanical power output by mechanical power decrease by of the fluid. That is what will gives the turbine, the efficiency of the turbine systems, and these are the basic powers. In terms of powers, also we have defined them as a efficiency components. Similar way, you can have a motor efficiency and the generator efficiency. Electrical power input for the motors, what is the mechanical power output? Motor generates from electric to the mechanical power. That is the reason you have a input is electrical power, output is mechanical powers, that ratios we get it. Similarly, way generators will have the mechanical power to electricals, but when you have a combined systems, pump and motors, then you have a efficiency of the both the systems you have to report, pump and the motors, that is what we will define it. Similar way, if you have a turbine and generators, you have efficiency of two the things which are independent. You need to know the combined efficiency, that means you have to have a multiplication factor for that, and that what is given here. Now, let us commit to the example problems, okay, which are GET and engineering service problems, which are very easy problems. Here we will apply mass conservations and Bernoulli's equations. That is all. We are not going to do much here. Mass conservations and the Bernoulli's equations, what will we use it, that is. But I always encourage you sketch the control volumes as well as draw streamlines. After the drawing the streamlines, apply the Bernoulli's equations for the 2 points. Okay. That to be looked at this part, and always highlight it. What are the assumptions behind that? What are the assumptions you have put it? That should be highlighted before solving any fluid flow problems. Now, look at this example 1, which is a constant in a pipe will cause the velocity to rise it definitely. Okay, there are just like a venturi meters here, there is a converging zones and the diverging zone. Okay, and because it is a converging zones, the velocity is to rise, its pressure to be fall it. That is what we know it. Very beginning of fluid Bernoulli's equations, the pressure difference is measured of flow rate through the pipe. The smooth neck down system shown in the figures is called venturi tube. Find expressions for the mass flux in the tube as a functions of the pressures and the pressure change, okay, which is very simple things. We will just highlight it how to use mass conservation equations and Bernoulli's equations. Now, let us sketch it. What are the flow classifications? Here we can assume it one dimensional flow, because incompressibles, steady and frictionless. That is what is our strength, because we are directly applying the Bernoulli's equations, as there is no energy loss components, we are not including that. Fixed control volumes, and we need to apply these Bernoulli's equations along a streamlines. The streamline shape could be like this. Okay, there will be converging zones and the diverging zones. The streamlines will be the converging and the divergings. Okay, or you put in the virtual fluid balls, you can have the tract of the flow path. The path lines of the virtual fluid balls also could be like this. Okay, they will converge it more or less parallel in these regions. So, there will be no curvatures of streamlines in these regions. Then there will be the divergence of the streamlines. Okay. So, that the flow structures what we get it in a venturi tube, and we need to compute it in terms of average velocities. So, we are not considering is turbulent or laminar velocity things, we are not putting any kinetic energy correction factors, which supposed to be done it, but in this case we have not done it. We just apply the mass conservations and the Bernoulli's equations, assuming that there is a uniform flow distribution. It does not happen like that. We use the average velocity here, and applying this as the tube is a horizontal, Z1 equal to Z2, you can write in terms of velocity difference in terms of pressure, and you apply the continuity equations to get it V2 in terms of pressure difference, and the beta, which is ratio between D2 and D1, representing the diameters at the sections 2 and the diameter at the sections 1 respectively. That is what we will get it, and finally, the mass flux will be rho AV, rho AV. So, area of at the sections 2 we know it, V2 we know it, then we can compute it what will be the mass flux. But please remember, as we have not considered energy losses, we need to incorporate a CD value, which is the coefficient of discharge to these the computations to find out what will be the actual value. This is what is m dot theoretical value, and this CD value comes from experimental study. The CD value comes from the experimental study. Let us have another examples, very interesting examples, that a body is moving with a still waters at 6 meter per second, produces water velocity 4 meter second at 1 meter ahead. That means there is a distance between these 2 points is 1 meters. This is what 6 meter per seconds. The flow is there is a reservoir type of conditions where the still waters are there, and the velocity at this point is 4 meter per seconds. Now we want to compute it. What could be the pressure difference between the nodes, and the point 1 meter ahead would be. So we can draw the streamlines which is passing through this point 1 and point 2, incompressible flow, steady, frictionless, irrotational in viscities. Okay. It is a moving control volume, but we are not looking at it as a moving control volume, we are just looking the pressure difference, we are not looking at the mass fluxes here. So, we will just apply the Bernoulli's equations between 1 and 2, because they are at the same horizontal levels, the Z 1 equal to Z 2, only we will have the pressure difference will be equate with the pressure head is equal to with the velocity head, and by substituting the pressures and the velocity, we will get it what will be the pressure difference. It is very simple problems, but only you have to visualize the problems, how it looks like this. So, you have to sketch for that. Third problems, which is very easy, the similar way as we discussed for the venturimeter problems in example 1, where in this is the GATE 2014 questions, where we have a venturimeters having a diameter 7.5 centimeters at the throat levels and 15 centimeter at enlarged is installed in a horizontal pipelines of 15 centimeter dia. Rate of the fluid pipe flow is 30 liters per second. The difference of pressure head measured between the enlarged and the throat locations is 2.45 meters. Find the coefficient of discharge of venturimeters. If you look at these problems, we already discussed in example 1, the same problems, only the numerical values are given for us to solve it. So, I will not take much time for these, only you can see that same streamline, you have to draw it and you apply mass conservation equations and the Bernoulli's equations to solve it, to find out, because here the actual discharge is given to us, we have to compute theoretical discharge. Once you know this theoretical discharge, you can compute the coefficients of discharge. So, this is a very simple things, again we are putting the mass conservation equations and the Bernoulli's equations, which is the energy conservation equations, and by just putting the substituting these, you will get a theoretical discharge and will get the actual discharge, you know it. So, you will get the CD value, which comes out to be 0.95. Another problems, we have a very interesting problems here, that is sudden enlargement of pipelines from 200 millimeter to 400 millimeters. The hydraulic gradient raises by 10 mm. Okay. It is just given that hydraulic gradient lines has increased by 10 mm, then we can estimate what will be the discharge in the pipe. So, again we will apply same mass conservation equation and the energy conservation equations along these streamlines. You can see that mostly the streamlines will be have a divergent and there will be energy dissipations on these systems, but let us, we do not know how much of energy dissipations, but we know it from data, there is the hydraulic gradient rise by the 10 mm. So, you have a mass conservation equations and considering the average velocity, not considering the kinetic energy corrections factors. So, we can know it, this mass conservation equations as you know it, A1 B1 equal to A2 B2, substituting these diameters we can get it a relationship between B1 and the B2, and then if I will substitute the Bernoulli's equations okay, along these constant lines. So, basically if you look at these two head, the pressure head and the Z1, Z2 is not given to us, but that is what will be reflected in terms of piezometric head. That's what is given. The difference between the piezometric head is 0.01 meters. So, we are substituting directly on that. We know this, the velocity and their relationship, we can compute the velocity. And once you know the velocity, we can compute the discharge. So, this way it is very easy problems. Only you have to look it has given the hydraulic gradient rise. That means, it is a representing us the pressure head and the elevation side. These two are, we are including it. When you put the two piezometers, what will be the raise? Because of that, that is what we have of 10 mm hydraulic gradient rise, and that is what we have substitutes. Let me conclude these lectures with the sense of balance of organ systems. If you know it, we know it, these ears is for the acoustic sound waves, that is the reasons we can hear it, and whatever I am speaking you can hear, because of the ear, which is sensory organ to uses the sound waves allow us to hear it. But this ear also have a compositions organ of balance inside the ear, which gives off the sense of balance. Like if I tilt it, I can get it from my brain, I am tilting it. Okay. That is what the sense of balance. I am not going to talk much details, but I am just telling you that the nature has given so beautiful arrangement of our body structures and the brain, which we cannot replicate it, and this is what it happens all in the fluid flow sensor organizers systems. So, that way we look at very smaller components what we teach in the fluid mechanics, but the human bodies, the structures still give us lot of lessons to be learned about the fluid, about the sensing organs and all. And that is the same things, and these times we talk about the kinetic energy corrections factors, how we need to be compute when you have the velocity distributions is uniform. And we also say in Bernoulliâ equations we can represent in terms of the pressures, static pressures, dynamic pressures and hydrostatic pressures, and two of the components I can represent as the stagnation pressures. And we also discuss about the hydraulic gradient line and the energy gradient lines and the mechanical energy and the efficiency. With this, let us thank you all for this patience here.